in this recording, we're going to be looking at some uniqueness theorems for rings and fields. We're going to start by observing that in the real number system, we happen to know that the additive identity 0, the multiplicative identity 1, and inverses, the additive inverse for A and the multiplicative inverse for A, are all unique. And what we want to do is we want to prove that this is actually true in any kind of a ring, or any kind of a ring with identity for the multiplicative identity 1. So our first theorem is going to be that we have R is a ring, and we want to simply say that its 0 element is unique. The way that we're going to prove this is that we're going to assume that we have not only 0 inside R, but also an element that I'm just going to call A inside of R. And we're going to assume that both of these guys are additive identities. So what does that mean? That means that we know the following things are true. We know that 0 plus x is equal to x plus 0, and that both of those things are equal to x for all x inside my ring. And we also know that a plus x is equal to x plus a is equal to x for all x inside the ring. And we know both of these things because that's the definition of additive identity. Now, what I'm going to notice is this. A is a perfectly good element of R. And so what that means is that A is part of this universally quantified statement. In other words, we can plug in A into this particular double equation. So the fact that A is in R is enough to imply that 0 plus A is equal to A plus 0, and that they are both equal to A. And this is because 0 is an additive identity. But I also want to note that 0 is a perfectly good element of R. And so I can plug in 0 into this particular universally quantified statement. In other words, I can make x equal to 0 in this particular double equation. So the fact that 0 is in R says that A plus 0 is equal to 0 plus A, and both of those guys are equal to 0, and this is because A is an additive identity element inside my ring. Now what I want to notice is that we've got A is equal to A plus 0, but we also have A plus 0 is equal to 0. Using those two boxed-in statements, we wind up getting the following important fact. We can say that A is equal to A plus 0, but A plus 0 is also equal to 0. So by transitivity, we know that A and 0 are the same thing, and that's enough to say that the additive identity in a ring is unique. Now, it's also important to realize that since fields are nothing more than a very special ring, we also know now that the additive identity of a field is unique. Now, it turns out that additive inverses are also unique. That's no surprise since that's how they behave in the real numbers. So let's actually get that theorem proved. So the theorem. Again, let's let R be a ring. Let's let A be any element of that ring. Then the additive inverse of A is unique. And the proof here uses the same technique as the previous proof. In fact, I would encourage you to stop the video for a few minutes and try and prove this on your own, and then start the video back up and see if you do the same proof that I actually go ahead and write down. So stop the video and try it. So hopefully you stopped the video and you tried to prove this on your own. Well, let's see. This is how the proof is going to work. We're going to let minus A and an element B inside R both be additive inverses for the element A inside my. So what does that say? That says we know the following by the definition of additive inverse. We know that A plus minus A is equal to minus A plus A, and that both of those things are equal to the 0 element in R. But we also know that because B is an additive inverse, we know that A plus B is equal to B plus A, and that is also equal to 0 inside of R. Now, what I want to notice is that I can look at that particular equation, and I can look at this particular equation, and transitivity of equality then lets me say that this mess here is equal to this mess here. In other words, using those two boxed equations, we can say that, let me go back to this color, that minus A plus A is equal to 0, which is equal to B plus A. So minus A plus A is equal to B plus A. Now what I'm going to do next is I'm going to post add minus A to both sides. And when I do, what we're going to get is this statement. We have minus A plus, let's make that a bit more readable, minus A plus A plus minus A is equal to B plus A plus minus A. Now I'm actually going to put in some parentheses because addition is associative. And when I put in those parentheses, what I get is I get the equation that says minus A plus 0 is equal to B plus 0. Well, that says minus A is equal to B, and that tells me that additive inverses are unique. Now, it turns out that one important idea about the additive inverse and the additive identity being unique is that it lets us conclude things have to be either the identity or the inverse if we happen to have something behaving like the identity or an additive inverse. In other words, what we can basically do is this kind of a thing. If we know that A and B are elements of a ring named R, and we happen to know that A plus B is equal to B, that's enough to let us say that we can conclude that A is indeed the 0 element of the ring. Likewise, if we know that A and B are both inside a ring named R, and I happen to know that A plus B just happens to be the 0 element, then I can conclude that the B just happens to be minus A. And both of these things are by uniqueness. Of the appropriate identity up here in this statement and the inverses in this statement. Well, we know that the real numbers are a field, and we know that inside the field of the real numbers that the multiplicative identity is unique. We know that multiplicative inverses are unique. And so I want to investigate them as well. But before actually doing this, I want to introduce a convention. When we have the phrase, R is a ring with identity, we usually write that in handwritten mathematics as R is a ring with 1. And what I'm trying to point out is that this is shorthand for the word with, and the 1 is shorthand for the word identity, because we're talking about a multiplicative identity. So our theorem is going to state if R is a ring with identity, then the identity element is unique. And again, the proof is just like the previous two proofs, so I would encourage you to stop the video and try and prove this all by yourself. So hopefully you've stopped the video and you've made an attempt to prove it. Let's now look at the proof together. I'm going to basically assume that both the known multiplicative identity 1 and some A inside of the ring are both multiplicative identities for R. So what does that tell me? That says that I know that A times X is equal to X times A, and both of those are going to be equal to X for all X inside my ring. And we also know that 1 times X is equal to X times 1 is equal to X for all X inside the ring. And we know both of those facts because these two things are both multiplicative identities, and these things are just the definition of multiplicative identity element. Well, now what we're going to do is we're going to note that A belongs to the ring. So what that means is I can plug in A for equal to X inside that universally quantified statement. In other words, I know that 1 times A is equal to A times 1, and that that's going to be equal to A. But I also know that 1 is inside my ring, and so I can plug in 1 into this particular equation because this equation is also universally quantified over all elements inside my ring. So what does that look like? So we have A times, we have A times 1 is equal to 1 times A is equal to 1. Now what I want to do is I basically want to be thinking in terms of looking at things. I've got that particular equation, but I also have that a times 1 is equal to 1. Using the two boxed in red facts, we can say that a is equal to a times 1, but a times 1 is also equal to 1. Therefore, a and 1 are the same thing, and as a consequence, what that says is that the multiplicative identity element of a ring or a field, because a field is nothing more than a special kind of a ring, must be unique. In other words, if a ring has a multiplicative identity, that multiplicative identity is unique. Well, now let's think about multiplicative inverse elements. Now, it's important to realize that in an arbitrary ring with identity, so in a ring with 1, some elements may have multiplicative inverses. In other words, some elements inside the ring have a partner element that we call A inverse, such that A times A inverse is equal to A inverse times A, and this is equal to 1 inside the ring. If an element has a multiplicative inverse, we call the element a unit in the ring. It's also important to realize that in a field, every non-zero element has to have a multiplicative inverse. So in a field, the only non-unit is the 0. So what we're looking at now is we're going to basically be looking at this particular theorem. So here's our theorem. Let R be a ring with an identity element. If A inside of R is a unit, if A is a unit, then its multiplicative inverse is unique. And again, I would encourage you to try and prove this for yourself. So stop the video, try and prove it for yourself. Hopefully you did that. Let's look at the proof. And it's very similar to the 3 previous proofs that we've done. We're going to assume that both A inverse and B are multiplicative inverses for element A inside our ring with identity. So what does that say? It says that I know that A inverse times A is equal to A times A inverse is equal to the 1 inside the ring. And because B is also a multiplicative inverse, I know that B times A is equal to A times B is equal to 1 inside the ring. Well, what I want to notice now is I want to look at this particular equation and this particular equation. Those two equations let me say the following. We have A times A inverse is equal to 1, which is equal to A times B. Well, that's enough to conclude that A times A inverse is equal to A times B. Now, what I'm going to do at this point is I'm going to pre-multiply by A inverse. I have to pre-multiply because I do not know that the multiplication is commutative. But when I pre-multiply by A inverse, I'm going to get A inverse times A inverse is equal to A inverse times A times B. But we are in a ring, and multiplication is associative, and consequently, I can change the placement of those parentheses and put them here on the left side of my equal sign. And I can change the parentheses over here and put them there. And when I do that, what I now have is 1 times A inverse is equal to 1 times B. But that last equation implies that A inverse and B are exactly the same thing. And so what this says is that multiplicative inverses, where they exist, are unique.